Following the half adder, we have the full adder circuit. The full adder is used to add more than 2 bits of information. So X, Y, Z are the inputs. C and S are the outputs. C, as told before, is the carry and S is the sum. The next step is obtaining the equations from the truth table. So wherever you get a 1, that has to be plotted in the corner map. So see the first corner map. This shows the corner map for the sum, and the second one is for the carry. The minimized expression for sum is given at the bottom of the corner map, and C becomes xy plus xz plus yz. This equation is implemented here, and we get the sum expression and the carry expression for the full adder. The full adder can also be implemented using two half adders. For that, consider the same truth table again, and these again are the expressions from the truth table. Consider the expression for S, or the sum. The first expression, x is equal to x bar y bar z plus and so on. That can be simplified into x XORed with y XORed with z. And C becomes xy plus z XORed with y. We get this logic diagram from the expressions. So when you look at the figure, the first highlighted portion is nothing but a half adder. The second highlighted portion is the second half adder. So the full adder has been implemented using two half adders and an OR gate. Next, we'll see about a binary adder or a 4-bit adder. A binary adder is a digital circuit that produces the arithmetic sum of two binary numbers. It can be constructed with full adders connected in cascade. The number of full adders depend on the number of bits. For example, consider this table. AI denotes a 4-bit number with A0 as the least significant bit and A3 as the most significant bit. And BI is the organ, B0 being the LSB, and B3 is the MSB. SI is the sum, S0 is the LSB, and S3 is the MSB, and CI plus 1 is the carry bit. So the carry which is produced from each stage is carried over to the next stage. Carry from the 0th position should be taken to the first stage. So each stage can be represented by a full adder, and the carry from the 0th position should be carried over to the first stage. The figure, each stage, as I had said before, is represented by a full adder. C1 is the carry out from the first full adder. It propagates to the full adder 2. C2, the carry out from the second full adder, goes to the third stage. And finally, C4 is the final carry. The next arithmetic operation which is being implemented is subtraction. While constructing a subtractor, the main points to be remembered are the inputs are minuend and subtrahend, and the outputs are borrow and difference. 4 rules are to be followed. Rule 1, 1 minus 1 is 0. 1 minus 0 is 1. Rule 4, 0 minus 0 is 0. It's a slightly different one. 0 minus 1 will be 1 with a borrow. So when you design the half subtractor, specify the function's inputs A, B, D, B, which I had explained in the previous slide. Step 2 is the truth table. The only line which is different is the second row. A is 0, B is 1. The difference is 1 and the borrow is also 1. So step 3 will be obtaining the equations. Consider the column D. D is 1 in row 2 and 3. So when you find out the function, it will be an XOR gate. And B is 1 only in the second row, which has A as 0, B as 1. So that will be A bar B. So this gives the logic diagram of a half subtractor. As said before, D is implemented using an XOR gate, and borrow out will be A bar B. A full subtractor will have 3 inputs and 2 outputs, difference and borrow. 2 table of the full subtractor is given. It is constructed using the 4 rules which were specified before. Obtain the expressions for D and B, and the logic diagram of the full subtractor will be like this. Many implementations can be had, but this implementation is done by using 2 half subtractors and an OR gate. So remember, a full adder can also be constructed by using 2 half adders and an OR gate.